Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, so today we will continue our lecture with chapter 3, Angle Modulation, Transmission and Reception, part 3. So this is the final part for chapter 3. So for chapter 3, chapter 3, part 3, we will cover the FM stereo, FM transmission, FM reception, average power of angle modulated wave, and finally the advantages and disadvantages of angle modulation compared to amplitude modulation. Okay, so without further ado, let's start with the FM stereo. So the first slide here is basically the history of FM transmission stereo, FM stereo. So basically, it all started before 1961. All commercial FM transmissions were monophonic. So this monophonic transmission actually means that it uses only a single 50 Hz to 15 kilohertz audio channel, where it is made up the entire voice and music information spectrum. And this audio channel modulated a carrier and was transmitted through a 200 kilohertz bandwidth FM channel. So the thing is, with mono transmission, even though we have two speakers, each speaker assembly at the receiver will produce exactly the same information. Thus, the entire information sounds as though it is coming from the same direction, meaning there is no sound directivity in monophonic transmission. However, starting from the year 1961, the Federal Communication Commission (FCC) has introduced what we call as stereophonic transmission. So the difference between stereophonic and monophonic, stereophonic uses a 250 to 15 kilohertz channel for the left and right audio speaker. So where the music originated on the left side is reproduced on the left speaker and vice versa. So because of that, this stereophonic transmission has a unique directivity and spatial dimension, and it is also possible to separate the sound by tonal qualities such as percussion, strings, and horns. So what can be concluded from this slide is that for the monophonic transmission, it uses only a single audio channel, while for the stereophonic transmission, it uses two audio channel for two left and right speaker. Okay, so for the monophonic transmission, there is no sound directivity, but for the stereophonic transmission, there's a unique directivity and spatial dimension for each speaker. So this figure here shows the FM baseband spectrum or the frequency spectrum. The difference for figure A is the spectrum prior to the year 1955. Figure B is the spectrum prior to the year 1961, and figure C is the frequency spectrum since the year 1961. So if you can see here is that prior to 1955, you only have a single audio channel, which uses a frequency between 50 Hz until 15 kilohertz. And then prior to 1961, it still uses a monophonic transmission with a single audio channel that uses a frequency between 50 Hz until 15 kilohertz. But now, it also introduced what we call as SCA channel subcarrier. Okay, so the function of the SCA channel subcarrier is basically to broadcast music to private subscribers such as department stores, restaurants, and offices. Okay, so for these private subscribers, they will use a frequency between 60 kilohertz until 74 kilohertz. And then since 1961, then only the stereophonic transmission is introduced. So if you look at here, instead of having one single channel, now it has the two channels, which is the left plus right stereo channel and also left plus inverted right stereo channel subcarrier. And then it also still have the SCA channel subcarrier, which used to broadcast the music to private subscribers. Okay, so basically the FM stereo started since 1961. So now let's focus on the FM stereo spectrum in figure C. So the FM stereo spectrum actually comprises of 50 to 15 kilohertz stereo channel, which is this part, plus an additional stereo channel frequency deviation multiplex into a composite baseband signal with a 19 kilohertz pilot and also a sub-stereo communication authorization SCA channel. So we have the left plus right audio channel, okay, and we also have the left plus the inverted right audio channel, this one, L minus R, and we also have the SCA channel. Okay. So the left plus right stereo channel occupies the frequency between 50 to 15 kilohertz passband. So this is the mono combination. While for the left plus inverted right audio channel, which is this one, it modulates a 38 kilohertz subcarrier FC and produces the left plus inverted right stereo channel, which occupies the frequency between 23 kilohertz until 53 kilohertz passband. And the last channel is the SCA channel that I already explained in the previous slide. So this SCA channel, this one, is used to broadcast music to private subscribers such as department stores, restaurants, and offices, where it occupies the frequency between 60 kilohertz until 74 kilohertz spectrum. So the identical information is contained in the left plus right and left plus inverted right except for their phase. So this figure is the block diagram for a stereo FM transmitter. So if you look at here, you have the left and right audio channel. This is the left and this is the right audio channel. So the left and right audio channels are combined in the matrix network. Okay, this is the matrix network. The left and right audio channels are combined in the matrix network to produce the left plus right and the left plus inverted right audio channel. Okay, so the left plus inverted right audio channel then modulates a 38 kilohertz subcarrier and it will produce a 23 kilohertz until 53 kilohertz left plus inverted right stereo channel. Okay. While the left plus right channel must be delayed to maintain phase integrity, so that's why you have a delay network here, with the left plus inverted right stereo channel for the modulation process. And then we have another 19 kilohertz pilot is transmitted rather than a 38 kilohertz subcarrier because it's easier to recover the pilot in the receiver. So the whole baseband signal is fed to the FM transmitter where it modulates the main carrier. So the next subchapter is the FM stereo reception. So basically the FM stereo receiver is the same as the standard FM receiver up to the output of the audio detector stage. Okay, so this is the block diagram for an FM receiver with mono outputs and stereo outputs. So the top part here is the output that generates the mono output, while the bottom parts here, the ones that generates the stereo outputs For mono section of the signal processor, the left plus right of the signal processor, the left plus right stereo channel, which contains all the original information, is simply filtered, amplified, and then fed to both the left and right speaker. Okay, so this is for the mono section. For the stereo section, this part, the left plus right and the left inverted right stereo plus inverted right stereo channels and the 19 kilohertz pilot are separated from the composite baseband with filters. Okay, so look at here, you have 3 filters. 1, 2, and 3. So the left plus right stereo channel is filtered by a low pass filter with an upper cutoff frequency of 15 kilohertz. While for the 19 kilohertz pilot is filtered with a high Q band pass filter multiplied by 2, amplified, and then fed to the left plus right demodulator. And then the third one, the left plus inverted right double sideband signal is separated with the band pass filter, okay, and then mixed with the recovered 38 kilohertz carrier in the balance modulator to produce the left plus inverted right audio channel. And lastly, the matrix network, which is this one, the stereo decoder, combines the left plus right and the left plus inverted right signals in such a way as to separate the left and right audio signals, which are fed to their respective speaker. Okay, so the difference is for the monophonic, the left and right speaker has the same, exactly the same information, while for the stereophonic, okay, the left and right speaker has a what we call as sound directivity. Okay, next part is the average power of angle modulated wave. So the average power of unmodulated carrier, we know that is defined as PC equals to VC squared over 2R, where VC is the peak unmodulated carrier voltage and R is the load resistance. Okay, so PC is the carrier power. And in order to calculate for the total instantaneous power in an angle modulated carrier, PT or P total is equals to the modulated signal squared divided by R. So MT is the modulated signal. Okay, so by substituting MT, you will get this equation. PT equals to VC squared over R cos squared omega CT plus theta T. Okay, and from this equation, you will get the equation 3. So in the equation 3, the second term consists of infinite number of sinusoidal side frequency components about the frequency equal to twice the carrier frequency. Therefore, the average value of the second terms is 0 and the average power of the modulated wave reduced to PT equals to VC squared over 2R. Okay. So what it means is that for the second terms here, okay, so this is a sinusoidal signal. So the second term here, this part, this is a sinusoidal signal. Okay, so if you take the average of the sinusoidal signal, you will get the value of 0 because it consists of positive and negative value. Okay, so that's why the P total here, because this term is already, this terms now is equals to 0. So since this terms now, the average is equals to 0, okay, so now your P total will become VC squared over 2R, okay, the equation 4. So equation 1 and 4I are identical, okay, equation 1 and equation 4 are identical. So the average power of the modulated carrier must be equal to the average power of the unmodulated carrier. So the modulated carrier power is the sum of the powers of the carrier and the side frequency components. Therefore, the total modulated power is Pt plus P0 plus P1, P2 up until Pn. So P0 is the carrier power, which is Vc squared over 2R plus, this is the side frequency, okay, 2V1 squared over 2R, because it's a side frequency, that's why you need to multiply with 2. Okay, so this is the second side frequency, third side frequency, and n side frequency. The power for the n side frequency. So you sum the power, you get the P total. So next is the final part, this final subchapter for chapter 3. So this is the difference between angle modulation and amplitude modulation. So first, let's look into the advantages of angle modulation compared to amplitude modulation. Okay, the first advantage is that the angle modulation has better noise immunity. Okay, we know that most noise in a communication system result in unwanted amplitude variations. Okay, so this frequency modulation and phase modulation receiver include a limiter that can remove most of the amplitude modulation noise from the received signal. Okay, so therefore, the frequency modulation and phase modulation, or we call as angle modulation, has a better noise immunity because it has a limiter that able to remove the AM noise. Okay, so the limiter cannot be used with amplitude modulation receiver because the information is also contained in amplitude variations, and removing the noise will also remove the information. So the second advantage is that the angle modulation has better noise performance and signal to noise improvement. So this is actually related to the first point here, where since angle modulation has a limiter that can remove the AM noise, so therefore the noise in angle modulation is lower compared to amplitude modulation. Therefore, the signal to noise ratio for the angle modulation is better compared to amplitude modulation. Okay, this is because the introduction of the limiters in frequency modulation and phase modulation. The third advantage is that it has better capture effect. It has a capture effect. So for FM modulation and phase modulation, a phenomenon of capture effect allows the receiver to differentiate between two signals and capture the stronger signal and eliminate the weaker one. While for the amplitude modulation, both signals will be demodulated and produce audio signal. And lastly, the advantage of angle modulation is that in terms of power utilization and efficiency. So when we compare with amplitude modulation, the carrier power remains constant with modulation, and the sideband power simply adds to the carrier power. So you need to add each carrier power for the, you need to add the sideband power for amplitude modulation. While for angle modulation, the total power remains constant regardless if modulation is present. Okay, and the power is taken from the carrier with modulation and redistributed in the sidebands. Okay, so that's the advantages of angle modulation. However, it still has some disadvantages. So the first one is in terms of bandwidth. So you know that for angle modulation, it has many side frequencies depending on its modulation index. Okay, so since it has many side frequencies, thus necessitating a much wider bandwidth compared to amplitude modulation. And the second one is that the angle modulation has a disadvantage of circuit complexity and cost. Okay, so the PM and FM modulator, demodulator, transmitter, and receiver is more complex to design and to be built. So because of that, since it's more complex, meaning it is more expensive. However, with the advent of inexpensive large-scale integration of ICs, the cost is comparable to their amplitude modulation counterparts. Okay, so basically that's the end of chapter 3. So remember, your midterm test will cover chapter 1, chapter 2, and also chapter 3, part 1. Okay, so that's the end of chapter 3. And next, we will cover chapter 4, which is digital modulation, in the next video. So thank you.